So now that we know a little bit more about aldehydes and ketones and we've discussed their physical properties, let's move on to discuss some of their reactions, right? Very similar to the setup we had for alcohols and a very common way to approach these different functional groups in these remaining chapters. Now with ketones and aldehydes in particular, we'll be looking at oxidation and reduction mainly. Those are the key types of reactions that we'll study in this part of chapter 14. If we think back to the previous chapter on alcohols, we said that alcohols are easily oxidized to aldehydes or ketones. Again, you have to be careful. If you're very aggressive in your oxidation of the alcohol, you might end up with a carboxylic acid, because as we see here, aldehydes are easily oxidized to carboxylic acids. So we have acetaldehyde there in the presence of an oxidizing agent, a fairly strong one, will give acetic acid. It'll give the carboxylic acid, which involves an oxygen in addition to that hydrogen off of the carbonyl carbon. So that's the slight distinction, and you have to be very careful when you're first picking these out. The carboxylic acid and aldehyde functional groups look very similar. If you're not counting your oxygens and paying very close attention, you might mistake one for the other, but that's the difference, and that's why oxidation of aldehydes would give carboxylic acids. Ketones cannot be oxidized in the usual way in the types of oxidizing agents we discuss in this course. Again, if you go on in advanced organic chemistry, you can find ways to oxidize ketones all the way up to carbon dioxide, but that's really harsh conditions. That's not very useful typically for what we would do. That's more an oxidation reaction in terms of a combustion reaction and not the type of oxidation we're looking for. All right, so if we follow this scheme here, we have ethanol, which is a primary alcohol, undergoing gentle oxidation to ethanal, and then ethanal, now an aldehyde, can undergo further oxidation to ethanoic acid, or acetic acid as we called it on the previous slide. Ethanoic acid being the IUPAC name, acetic acid being the common name. Again, we'll save the naming for our chapter on carboxylic acids. So as I mentioned before, you have to be careful because if you took that ethanol and put it in a harsh oxidizer, you might go right up to the ethanoic acid because you might not be able to stop it at the aldehyde stage. So use a gentle oxidizing agent to make that first oxidation, and then a stronger oxidizer to accomplish the aldehyde to carboxylic acid oxidation. If we look down below, we have now 2-propanol, a secondary alcohol, and we can oxidize that up to propanone, but we don't typically see any further oxidation because the oxidizing agents we would use wouldn't be able to oxidize it further. It's got carbon-carbon bonds on either side of that carbonyl, and it's not prone to oxidation like the aldehyde, which has that carbon-hydrogen bond that can be oxidized to a carboxylic acid. Now, aldehydes and ketones both have that carbonyl functional group as their key feature, but as we just saw, aldehydes will oxidize and ketones will not under normal conditions. So one of the ways that we can distinguish whether we have an aldehyde or a ketone is to perform a test like the Tollens test. In the Tollens reagent, there's silver 1+, and that can oxidize the aldehydes to carboxylic acids, but it will not oxidize ketones. So that's a nice way to be able to determine whether you have an aldehyde or a ketone. The Tollens test is also a very beautiful test because the silver ion is reduced to metallic silver during that oxidation step, right? As the aldehyde is oxidized to carboxylic acid, the silver is reduced to metallic silver, and it makes a mirrored finish in the test tube. So it's a very, very pretty one to do in a face-to-face laboratory setting. And so here we see that Tollens test is a very specific test and can be used to distinguish between an aldehyde and a ketone. What's nice is it won't oxidize alcohols or ethers, so it's pretty specific, at least in terms of the functional groups we've learned so far. And here we see a balanced, well, at least a semi-balanced reaction where we have the ethanol, the acetaldehyde, interacting with 2 moles of silver 1+ from the Tollens reagent for every 1 mole of ethanol to give 2 moles of metallic silver that give that silver mirror finish plus 1 mole of ethanoic acid or acetic acid as it's known. So it's not a complete reaction because we don't find out too much information about that oxidizing agent. It's just the O in brackets above the arrow, but it does give us all the other details and explains why we would see a silver mirror for ethanal, but not for 2-propanol, 2-propanone rather, sorry, or 2-propanol. Yes, the alcohol there. Okay, so we see it with the aldehyde, but not with the alcohol or with the ketone or ether. Now the Talens test is quite effective and very beautiful with the silver mirror, but it is fairly expensive. So there are some other tests, and one that we'll discuss now is the Benedict's test. In the Benedict's test, you have copper 2 ion reacting with aldehydes that have an adjacent OH group. So here we have to be careful because it's not going to be any aldehyde, it's going to be even more specific. So you could either use it in place of the Talens test if you know you happen to have this structural feature, or more likely you would be able to perform the Talens test first to determine you have an aldehyde, and then the Benedict's test would tell you if you have an aldehyde with an adjacent hydroxyl group. The aldehydes are oxidized to carboxylic acids again, just like in the Talens test. In this case, instead of silver being reduced to metallic silver, we have copper 2+ ion being reduced to copper 1 oxide. And that's on the right hand side. You see that beautiful copper 2 is that pretty blue color, and then the copper 2 Cu2O, which is really copper 1 oxide because it's 1+, is that sort of brick red color. Now, the reason we're talking about all these tests in terms of aldehydes and ketones is getting ready for our discussion of carbohydrates in an upcoming chapter. So many sugars, such as glucose, contain the type of aldehyde grouping, so the Benedict's reagent can be used to determine the presence of glucose in blood or urine. So the type of aldehyde that glucose is has that adjacent OH. If you look at the aldehyde carbon, the carbon of the carbonyl, the neighboring carbon has an OH group on it. So therefore, as we react glucose with copper 2+ ion in the Benedict's test, we'll see that brick red copper 1 oxide form, and we'll also have now the carboxylic acid, which is gluconic acid from glucose. And those D's are going to become pretty important toward the end of this chapter, but we'll hold off on that for now. Let's pause here for a learning check, see how you're doing with these concepts. This learning check asks that you write the condensed structural formula and the name of the oxidized product when each of the following is mixed with Talens reagent. So butanal, acetaldehyde, and ethyl methyl ketone. So go ahead, write the condensed structural formula, or better yet, the skeletal structure of the product and name it for each of those interacting with Talens reagent. Pause the video here while you do that work and start us back up when you're ready to check your work. All right, so butanal would be a 4-carbon species with that last carbon or first carbon, depending on how you drew it, being the carbonyl carbon with an H attached. Because it is a ketone, I'm sorry, yeah, it's an aldehyde rather, it's going to interact with Talens reagent, the silver 1+ ion, to form the carboxylic acid. So now we have butanoic acid, which the 4 carbons that caused the name to be butanal, now we change the name to butanoic acid, and in addition, the structural change is an O in addition to the H. So C double bond O, single bond OH, whereas before it was C double bond O, single bond H at the end. For acetaldehyde, that would be, again, a 2-carbon species, and we do the same sort of thing. One of the carbons had the carbonyl and a single bond to hydrogen, and now we've oxidized it to have a single bond to oxygen and then a hydrogen. So that would be ethanoic acid or acetic acid as it's commonly known. Finally, hopefully you didn't get tricked here with C, ethyl methyl ketone. As a ketone, it would not undergo oxidation with the Talens reagent, and therefore there'd be no reaction and no need to draw or name a product. So hopefully that went well. If you got caught there by the last one, don't worry about it. You won't get caught again, I'm sure, because you've learned that lesson now. So up until now, we've discussed the oxidation of aldehydes and the fact that ketones don't oxidize under normal conditions. So here's a chance to discuss the reduction of aldehydes and ketones, give the ketones some chance to react here. So aldehydes and ketones can both be reduced by either hydrogen with a catalyst or by sodium borohydride, NaBH4. And as a result, you'll decrease the number of carbon-oxygen bonds, right? That's one of our definitions of reduction in organic chemistry. Finally, we'll reduce aldehydes to primary alcohols, right? Because if we look at propanal there, we're going to have a carbon that's double bonded to an oxygen, single bonded to a hydrogen, and then single bonded to a carbon group. That's classic aldehyde. When it interacts with that hydrogen in a platinum catalyst, it's going to add 2 more hydrogens to that carbonyl carbon. So one goes to the oxygen to make an OH group, which is why we get an alcohol. The other goes to form a CH bond, and the reason we get a primary alcohol is because now we have just one carbon-carbon bond as we did before in the propanal from the carbonyl. If we look at ketones, we can reduce ketones under the same sorts of conditions to secondary alcohols. So we see here propanone, we add hydrogen to it in the presence of a nickel catalyst here. We see the same sort of feature, that carbonyl C double bond O gets reduced to a C single bond OH and a C single bond O, and because the ketone was had the carbon of the carbonyl bonded to 2 carbon groups, the alcohol now will also be a carbon that's bonded to 2 carbon groups and therefore yields a secondary alcohol. Okay, so before we leave this chapter section, let's go ahead and end with a learning check. In this learning check, you will predict the product for each of the following reactions. So in the first case, we have an aldehyde. The second case, we have a ketone. And if you would please go ahead and stop the video here, complete the reaction with the products, and start back up when you're ready to check that work. Good luck. Okay, so in the first case with that reduction of the aldehyde using hydrogen on a platinum catalyst, we get the primary alcohol, right? We take that C double bond O and reduce it to a C single bond O with an H attached, or as we show it here, just a COH bond. And then we add another H to give carbon the 4 bonds on that former carbonyl carbon. For B, same sort of thing going on. We take that carbonyl carbon, we reduce it to a single bond oxygen with an H, and then another hydrogen carbon bond that we don't show here because this is a skeletal structure and we'd only show H's when they're parts of functional groups like carboxylic acids or here secondary alcohol. Hopefully that was nice and easy for you. If it did give you some trouble, please try some additional practice problems on reduction reactions of aldehydes and ketones. If you're still struggling, then reach out to me for some help. Otherwise, if things are going well, as I hope they are, we'll see each other in the next section of Chapter 14.